by the end of discussion in this video, you will have a great deal of information and knowledge about the backbone of transformer-based large language models. And this backbone or secret mechanism is called attention. So not only you will be able to appreciate the capabilities of such large language models, but would also be able to lay a solid foundation in tokenization and embeddings, which are the pre-processing part before the input can be handled by attention mechanism. And also you would be in a state where you would be able to explore under the hood stuff. Hey everyone, welcome back to the channel. So before we can start any discussion on transformers and attention, I want your affirmation on two statements. I have two statements and I want your affirmation that my interpretation is correct or not. You can put that in a comment box. So when I say that I cannot wait for spring to arrive, and when I say the spring of the mattress is broken, so there are two spring words into different context, into different sentences. So in the first statement, when I say the spring, I cannot wait for the spring to arrive, what I essentially mean is that I'm talking about the season. I cannot wait for the spring season to arrive without explicitly mentioning the word season. And in the second sentence, when I say that the mattress spring is broken, what I essentially mean again is that I'm talking about a coiled metal device without giving any context about what the spring in the mattress is and what the spring in the season is. As a human, it comes very intuitive to us. But how can a machine model differentiate between such context? How can I tell the difference that the spring used for the season and the spring used in the mattress differ in context, differ in semantics, differ in hierarchy, and differ in entire presentation of the sentence? So, we do not pay attention to such words or such context because they comes very easy to us. We can clearly make sense of it. But machine models or large language models needed attention. So that is what we will be discussing, the attention mechanism. It is going to be a multi-part video series in which we will start with something very fundamental like tokenization, embeddings, and then we will explore the QKV framework, which is query key value algorithm, which helps to find the machine model, the relationship between different words, and able to relate the importance of each word with respect to each other. So the advantage of knowing inner workings and under the hood stuff is that you can interact with the model in a very efficient and productive manner. So by knowing the inner workings and how the model behaves and how the model processes the data, you will be able to formulate better prompts. Prompts are their way of conversing with the model. The better you understand the inner workings of the language model, the better your prompts are. So you can formulate a framework around your prompts and can better interact and converse with the language model. And you would be able to greatly increase the chances of getting the required and desired outcome from language models. So believe me, I'm very excited to explore all of this under the hood stuff with you in this multi-part video series. So without much ado, let's jump right at it. Let's start our discussion with an important characteristic of attention, which is attention blocks just do not accept raw text or as is input that we provide to the model. It has to be in a format understood by the attention. Therefore, before the input can enter attention blocks, input needs to be primed and has to be pre-processed in a format required by attention blocks. At a high level, we can think of it as the translation box where the text enters as words, which are then broken down into smaller units called tokens. There are different tokenization mechanisms. Also, the today's discussion in this video is focused on different tokenization mechanism. Continuing with the next step in this input processing is token embeddings. In token embeddings, these tokens are then assigned a numerical identity and essentially help to capture the meaning of each word and allows the model to understand the relationship between them.
And the next step is positional encoding. We can think of positional encoding as adding a location tag to each word, since transformers do not inherently understand the order of words, and therefore positional encoding provides them with this information. It is like adding a bit of extra data to each word's embedding, telling the model where it sits in the sentence. Now think of an example like I love pizza and I pizza love. Here the words order changes the semantics, and by maintaining the word orders, this positional encoding helps retain correct semantics. Finally, the processed input is passed to the attention block for further processing. Alright then, let's quickly observe this behavior through a transformer simulator. To this model, I provided a text string, which is I want to learn LLM, so that I deliberately left this sentence as open ended just to showcase in later videos what all probabilities the model predicts and why it will choose a certain output over others. Now, let's see what all this translation box contains. As discussed a moment before, we can notice this input getting broken into smaller chunks as tokens, and then token embeddings assign a numerical identity to these tokens, and finally, positional encoding adds some spatial dimensional data so as to make discovery of these tokens feasible. I want you to pay some attention to how the model has further broken the word LLM into further subwords or characters, and how different tokenization mechanism handles a text which is not part of general vocabulary. While the actual processing of embedding is quite complex and has much more complex technical details, but this simplified representation essentially captures the underlying concepts and building blocks of LLMs. Having built some context around embeddings and tokens, let's now discuss the tokenization process and important tokenization mechanism. As we observed earlier, tokenization is the process of breaking the text into its atomic units, and these units differ with different tokenization mechanism. And the first such mechanism is word-based tokenization. Word-based tokenization adopts a straightforward approach by splitting text on white space or on punctuations. It is generally easy to set up and can be used with only a few rules. Imagine training a machine model to understand the phrase, the cat sat on the mat. A word based tokenizer would split this into individual words and then assign each word a unique number. Seems simple and intuitive, right? But with this kind of tokenizer, the drawback is that we end up with some pretty large vocabularies where a vocabulary is defined by the total number of independent tokens that we have in our corpus. In this mechanism, each word gets assigned an ID starting from 0 and going up to the size of the vocabulary. Just imagine, in order to cover a language with a word based tokenizer, we will need to have an identifier for each word in the language, which will, of course, generate a huge amount of tokens. Now, consider any library of classic novels, academic works, etc. So, tokenizing literature work would require hundreds of thousands of unique tokens, but the English language itself contains over a half of million words, thus creating a huge vocabulary size. And this is not just about English. What about vocabulary of other languages not having Latin as base? And therefore, this means that in order to understand multiple languages, the model needs to be trained specifically for each language, thus adding more and more tokens. But this is not just one disadvantage. To make it even worse, word based tokenizers miss obvious connection between words. For example, words like write, writing, and wrote are treated as completely unrelated tokens, forcing our model to learn relationship of such words from scratch rather than recognizing their shared root. And what happens when we encounter words outside our vocabulary? We are then forced to use a special UNK token, a non token, essentially telling our model that something meaningful was here, but I cannot tell you what was that, leaving the model with incomplete understanding. Also, too many such UNK may even mean that the model wasn't able to retrieve a sensible representation of a word and you are losing information along the way. Therefore, the goal when crafting the vocabulary is to do it in such a way that the tokenizer tokenizes as few words as possible into the unknown token, but this mechanism does not fulfill this requirement and may be used only for domain specific models. I tried this mechanism practically with an overtly simple version and trained the model with just 10,000 word corpus. I personally found the model training part tedious and full of inconsistencies. But this is not generalization and may differ how efficiently you write or use training code. To highlight one specific use case, I had to use uncased and cased parameters as same words but with different cases were treated as different tokens. I will put this entire code and output on my GitHub repo and make it even public and also share it in my video description very soon. That's all for today, guys. I hope you liked the video. In the next video, we will cover a detailed comparison of byte pair encoding and its different flavors used by ChatGPT, Llama, and DeepSeek, etc. We will also discuss on how the problem of UNK tokens were handled by another tokenization mechanism, which is character-based tokenizers. And then we will discuss the mechanism which used the best of both character and word based and now used by almost all modern LLMs like ChatGPT, Gemini, and DeepSeek, etc. So stay tuned for more content like this. See you around.